Hi, welcome to the session. In the last session, we have discussed about the methods of generation of EMF, some questions on stationary induced EMF especially we have discussed, and we discussed about Lenz's law, how to find the polarity of induced EMF, and we did some questions based on the stationary induced EMF. Okay, so let us move on to the next important topic, that is called construction of the transformer. Okay, right. So if you look at construction in the very initial session itself, I said if you look at whatever the machine, whether it is transformer, induction machine, DC machine or synchronous machine, there are two parts you can see. What is magnetic path, another one is conductor or winding. One is magnetic path, another one is winding. So here the major two parts are, let me take up a fresh page and I will tell you. The major parts in any machine are here magnetic path and windings. Okay. So we will be discussing about first magnetic path here. I said, I can say magnetic path. The purpose of magnetic path is to create the flux lines. The purpose of magnetic path is to carry the flux lines. Okay. How do you create this magnetic path? One is, you can take a permanent magnet. You can take a permanent magnetic path, or because the main intention of this path is to carry the flux lines. The main intention of the magnetic path is to carry the flux lines. So why don't you take up directly a permanent magnet is a question. Now another one is electromagnet. So here I will be taking the permanent magnet. So if you take a permanent magnet, flux is constant. If you take a permanent magnet, flux is constant, not time varying. If you take up electromagnet, and electromagnet also AC excited and DC excited will be there. So in AC excited, flux will be variable. In DC excited, flux is again constant. Okay, of course, but here you can have a chance to vary the flux with the help of voltage. So this flux also variable if it is possible. If the DC voltage variable, now this is also variable. But in permanent magnet case, you cannot vary. That's the reason why we don't prefer permanent magnets in any instruments. We always use electromagnets. Okay, we don't prefer permanent magnet. Okay, so that electromagnet can be energized with AC or otherwise DC supply. Let us see here, we need a time varying magnetic field to produce a EMF. To produce EMF, we will be taking a time varying magnetic field, that is AC excitation we will take up. Okay, so let me show you here. To produce a field lines, I am taking here a coil, and this coil is energized with an alternating voltage source. This alternating voltage source is going to drive a current I of t, and this I of t is going to create a flux phi of t. Okay, maybe like this it is going to create. Okay, so this is how the flux lines are going to be, time varying flux lines are going to be. Now these time varying flux lines are going to establish in this direction. Some flux lines are in the right side, some flux lines are in the left side. Okay, if these total flux lines are, if you take up them as phi 1, some flux lines are diverting onto the right side, some flux lines are diverting onto the left side based on the reluctance. As a coil is air core coil, some flux lines will establish on the right side, some flux lines will be on the left side, because around the coil air is there. The reluctance offered by the air gap on this side, the reluctance offered by the air gap on this side will be same. That's the reason why the flux division may be probably 50% on this side and 50% on this side. Okay, let me take up here the source separately for lengthy. I'll take up the source and little away from this one. Let me take up. This is my source V of t. Okay, so now the flux lines can be drawn like this: 50% on this side, 50% on the right side. because the air around the coil is going to offer same amount of reluctance for the flux lines, and this is how it is going to be existed. So this is my electromagnet. If the voltage is time varying, current is time varying, and the flux also going to be time varying. If the voltage is constant, DC polarity, current is constant, the flux is also constant. Okay. Why don't we use permanent magnets? If you use permanent magnet, flux is all the time constant. Okay. EMF depends upon the flux lines. If you want to change the output, flux has to be changed, na? If you want to increase the EMF, flux has to be increased. If you use permanent magnet, you cannot increase the flux and you will be losing the control over the EMF or output. It is better to have as many controls as possible on the output. So we never use permanent magnets in the large size machinery. We use electromagnets. Okay, so electromagnet can be energized with AC supply, can also be energized with the DC supply. Okay, for DC supply, what you have to do, what you will be doing is, you will be keeping a potentiometer, or otherwise you will be keeping a potential divider, and with that potential divider you can increase the voltage, and the flux also changes according to the applied voltage. By the way, as the flux lines are linking with this coil, definitely an EMF is going to be induced in this coil. This EMF we call it as stationary induced EMF because the coil is stationary, and also I can also call it as self-induced EMF because the own coil flux lines, let me take up it as N1 turns. N1 coil flux lines are linking with N1 only. Therefore, I can call it as self-induced EMF. If myself can slap myself, if my hand slap myself, if my hand slaps my cheek, then I'll get pain. So EMF induced in me, it's self-induced EMF. If my hand slaps another person, then EMF induces in him. That's a mutual induced EMF. That's a pain in another person. Okay. So here the self-induced EMF, if you look at the self-induced EMF, now I am taking this terminal as common. Now I wanted to drive certain amount of load here. The load can be, I am connecting like this load. The load terminal can be connected at this point, can be connected at this point, can be connected at this point. So these are tappings. If you put the tapping at the minimum, the voltage across the load is minimum. If you increase the tapping, the voltage across the load increases. If you increase the tapping, the voltage across the load increases. At maximum, the voltage across the load at maximum is equal to supply voltage. You cannot go beyond that. This is the same as like an auto transformer condition. At maximum you cannot go, at maximum you can get supply voltage. You cannot go beyond that. So load voltage cannot be greater than the source voltage. For example, if I have a load of fan of 230 volts, but my source value is 200 only, I cannot drive the fan with the 200 volts this transformer or this coil. Okay, so the drawback with this self-induction mode of power transfer or else conduction, self-induction mode, self-induced EMF, this load is driven by self-induced EMF. So self-induced mode, self-induced EMF cannot drive the loads which are greater than the source voltage rating. That is a drawback. And one more drawback is here, if suddenly there is a short circuit, if there is a fault, abnormal condition. Now this short circuit is directly connected, it's an electrical connection. It's directly at short circuit across the source. You are creating a short circuit across the source. Therefore, the source is going to drive a very huge current and it will be leading to a failure. So this is the biggest drawback on this kind of connection. That is the reason why what we do is we don't use self-induced EMF to drive the loads. To avoid the shocks, direct short circuit, and moreover, if the load voltage is greater than the source voltage, we cannot use this one. Therefore, we are taking one more coil. Near to that coil, we will be taking one more coil and we will be energizing it. Okay, let me take up this voltage source, supply voltage as 100. Okay, now I am taking one more coil on this side. Okay, so if I take up 100 turns here, now if I take up 200 turns or 300 turns here, N2 will be greater than N1. Why? I am suffering from I'm suffering from low voltage. Okay, I'm getting low voltage. I want more voltage. If I wanted to drive the load of, here 300 volts load or 400 volts load, whatever the load voltage you want to drive, you can use that kind of number of turns. If you increase the number of turns, EMF increases, because EMF is equal to N into d phi by dt. Okay, if the number of turns increases, the voltage across the load is going to be greater than this time greater than the source voltage. Now, can't you decrease the voltage? Yes, you can decrease the voltage. If you provide the tapping on this one, you can get less than 100. Sorry, you can get you can get less than 100. You can get greater than 100 also if you provide tapping on this one. So this connection is helping us to get the voltage lesser than the source voltage. Can also helps us to get the greater than the source voltage. Okay, so that is the reason why we are going to use another coil, and whenever it is carrying a current, whenever this N1 coil is carrying the current, that is going to produce a flux lines like this. Okay, right. Now out of these two flux lines are diverting onto the right side and two flux lines are diverting onto the left side. Okay, like this. Some part of the flux is diverted onto the left side, some part of the flux is diverted onto the right side, because the air gap around the coil is same. So I can say that the reluctance offered for the flux line is going to be same. So half flux is divided on this side, half flux is divided on this side. Now out of this phi 1, some part of the flux is linking with the coil 2. I can call the flux lines as phi 1 2. The coil 1 flux lines linking with coil 2. Phi 1 2. Now the induced EMF in this coil is not going to depend upon phi 1, is going to depend upon, so E2 I can write it as N2 into d phi 1 2 by dt. d phi 1 by dt. Even though the number of turns are more, but the flux linkages, mutual flux linkages, okay, the flux linkages with the coil 2 is less than the coil 1. If the flux linkages with respect to coil 2 are lesser, then it leads to again low voltage. What is the use of having high number of turns? If you can divert all these flux lines onto the right side, if you can divert all these remaining 50% flux lines onto the right side or onto the N2 coils, then the mutual flux linkages will increase, or the coupling, the flux lines coupled to the other coil increases. We call that as coefficient of coupling. If the coefficient of coupling can be enhanced, then the EMF also can be enhanced. Why is it not happening? Because air gap around the coil on both the sides, it is same. Reluctance offered for the flux line, it is same. Whether you keep here, if you keep near the coil, if you keep the coil very near, then also some 50% flux lines links here, 50% flux lines links here. If you keep it away, the phi 1 2 strength decreases. If the coil is kept away from the primary coil or coil 1, then phi 1 2 strength decreases. If the phi 1 2 strength decreases, because the flux line has to establish for a longer distance now. If the air gap is more, reluctance is more. If the reluctance is more, flux strength decreases, then the EMF strength decreases. Don't keep the coil away from the first coil. And moreover, try to convert this remaining 50% of flux lines onto the right side or coil 2. Then the mutual EMF can be enhanced. How can it be done? It can be done by providing, if you are expecting the flux lines onto this side, that means what? This path, the path between the turns should have a low reluctance path, should have a less opposition, should have a high permeability. That path should allow the flux lines easily. Then you can have coupling coefficient can be enhanced and EMF can be enhanced, and that is done with the help of magnetic path. The magnetic path purpose is to establish the flux lines easily between the two coils. Here I have a coil 1, and the coil 1 is carrying the current, and therefore the flux is producing. Here, whatever the flux lines which are produced, 99% of flux lines are established in the core now, because the core is offering low reluctance. Yes or no? Now only hardly 1% flux line is going to be existed, leakage flux. Leakage flux, here it is going to be 1% hardly. Because 99% of flux line is establishing through core. Now if you place a winding here, if you place a winding here, if you place a winding on this side, then 99% of flux line is linking with the coil 2, 100% flux line is linking with coil 1. The mutual flux linkages, here it is going to be increased, N2 into d∅12 by dt. Now compared to the previous case, the mutual flux linkages are increased. The coefficient of coupling is increased. K decides ∅12 out of 100% flux line, how much amount of flux line is linking? 99% flux is linking. So coefficient of coupling is 99%. Keeping the magnetic path enhances the coefficient of coupling. Magnetic coupling, the magnetic coupling is going to be increases. Okay, then if you are expecting, if you want to increase the magnetic coupling, how should be the core? How should be the magnetic path? The magnetic path purpose is here. The magnetic path purpose is to carry the flux, lines. Okay, to carry the flux lines, this magnetic path must be this core must be a magnetic medium. What is a magnetic material? The magnetic path or core should be designed with ferromagnetic material. Should be designed with ferromagnetic material. Why ferromagnetic material? Because ferromagnetic material is a superior form of magnetic material. It possesses high permeability and low reluctance. If you look at ferromagnetic material, it will be, let me show you the ferromagnetic material structure. Let me show you the dipoles here. Like how in a conductor, how the electrons are randomly they tries to move here and there because of room temperature, how randomly electrons are going to be existed. In the same way, in the ferromagnetic materials also, the magnetic poles are going to be established like this. Okay, the dipoles are going to be established like this. Now, this is a magnetic path. Now, what I want to do, I want to magnetize the core. How can we do that? We are keeping the winding on this core. Let me keep the winding here. And this winding is carrying the current. Every current carrying conductor is going to produce a magnetic field. So this is also going to produce a magnetic field in this direction, in this direction, in this direction. So this is the supply flux lines, current carrying conductor flux lines. Now the current carrying conductor flux lines are trying to establish through low reluctance path. The low reluctance path is this one, ferromagnetic material. Okay, now this magnetic flux line is magnetizing this dipole and changing its orientation. Is magnetizing this dipole and changing its orientation. Is magnetizing this dipole and changing its orientation. Here also, all the dipoles are going to change its orientation according to the external magnetic field direction. Now, if all the dipoles are changed according to the external magnetic field, then I can say that complete magnetization is done. Effectively, the magnetization is completely done. The core is magnetized completely. Now, to magnetize the core completely, the force demanded, the energy demanded by this core is going to be very, very, very low, because it is a ferromagnetic material. Here, the flux establishment, the dipoles are arranged, the dipoles are oriented according to the external magnetic field direction. In order to change its orientation, the energy consumption by this material is going to be very less. That is what hysteresis energy or hysteresis loss. And the flux lines the dipoles can easily establish. The dipoles are not drawing a very huge amount of force. It is drawing very least amount of force. I can say that the magnetizing current drawn is going to be very, very less to change the orientations, because the permeability is very, very high. Permeability is like, the magnetic path, how easily the flux lines are going to be allowed. Permeability defines the easiness of flow of flux lines. Okay, so ferromagnetic material is going to ferromagnetic material offers high permeability and low reluctance. Okay, high permeability and low reluctance. High permeability is nothing but easiness of flow of flux lines. Easiness of flow of flux lines. Or it's not, flux lines cannot flow. We can say that easily, the easiness of flux lines, establishment of flux lines. Okay, ferromagnetic material can offer high permeability and therefore it draws very small magnetizing amount of current. Moreover, the hysteresis coefficient is low. X value is low. Hysteresis coefficient X is low. Generally, it will be around 1.6 for steel or 1.2 to 2 range. Okay, if hysteresis coefficient is low and the energy consumption for the orientation of dipoles is also less, so I can call it as hysteresis loss. Hysteresis loss is also less. So core has to provide these property, these features. So what is the magnetic path intention? The magnetic path intention is to carry the more flux lines onto the secondary side. How it can carry? If you can design with the magnetic path, if you can design the magnetic path with ferromagnetic material. Now what a ferromagnetic material offers? The ferromagnetic material offers less reluctance, high permeability, less hysteresis coefficient and less hysteresis losses. Okay, so that is the reason why we choose ferromagnetic material or otherwise steel. Ferromagnetic material, who is that? What is that? Steel. So steel offers high permeability, low reluctance and this hysteresis coefficient is 1.6, hysteresis loss is also less. By the way, what we do is, along with the steel, we add up some silicon content. Then it has become silicon steel. So the magnetic path of any not only transformer, whether it is an induction motor, whether it is a synchronous machine, the magnetic path is designed with silicon steel. The presence of silicon has some function. Silicon is not a magnetic material. Silicon is a non-magnetic material. Silicon is a non-conducting material. Silicon is a non-magnetic material. Non-magnetic and non-conducting material. Then why are we adding the silicon to the steel? What is going to happen? What is going to happen in the steel? So I have taken it as steel and I have so many dipoles here like this. The dipoles are going to be energized here. Let me take up here external magnetic field. This is external magnetic field direction. Now internal dipoles are going to be like this. Okay. Now whenever you give the supply drives a current produces a flux. This is the flux direction. And now these flux lines are trying to magnetize the core. Now inside the dipoles are going to consume the energy like this and change its direction. While the magnetization is happening, as core is not 100% perfect magnetic material, definitely few electrons are available. There are chances of getting availability of electrons here and there. Okay, therefore, whenever the magnetization is happening, what is going to happen? On the free electron, this magnetic field will create a force on the free electron. That force tries to move the electrons from one place to another place. And this movement of electron, we call it as eddy currents. This movement of electrons, we call it as eddy currents. Eddy currents are because of presence of electrons in the core. Core purpose is to carry the flux lines, not to carry the current. So as the magnetic properties of the core, not 100% perfect. 99% magnetic properties are there, 1% conducting properties are there. Due to that impurities, electrons are presented, free electrons are existed. And now whenever the magnetization is happening, on the free electron, whenever the magnetization is happening, a force is going to be created. And that force is trying to move the electron from one place to another place. Force is nothing but what EMF is going to be induced. Now the EMF is going to drive the electrons from one place to another place, and that leads to eddy current, and this eddy current leads to eddy current losses. So here inside the core, to change the direction, to change the orientation of the dipole, it will consume some amount of energy. Magnetic path will consume some amount of energy. And to drive the electrons also, it will consume some amount of energy. This is called eddy current losses, and the energy consumed for the establishment of poles, maybe in the positive half cycle, maybe in the negative half cycle, we call it as hysteresis loss. Energy consumed by the poles for the establishment, maybe reversals, for consumption of, to reverse the polarities, maybe north pole to south pole to north pole. It will consume the energy. So hysteresis loss, eddy current loss is there. We call them as core losses. Now these two losses has to be supplied. These two losses has to be supplied. Okay. Anyhow, that is okay. Has to be supplied by the source only. The two losses has to be supplied by the source only. Now the point is here, as we are getting eddy current, you will get a heat dissipation. That heat dissipation can disturb the magnetic properties. In order to minimize the eddy current losses, what we do is we add up silicon grains here. We add up silicon grains here. This is the silicon. Silicon is a non-magnetic, non-conducting medium. When you add silicon to the core, it leads to increment in resistance. Because of presence of silicon to the core material, now the addition of silicon increases the resistance. If the core resistance increases, then it leads to eddy current loss, strength of the eddy current decreases. If the strength of the eddy current decreases, then the eddy current loss also decreases. Okay, here don't add more and more amount of silicon steel. The addition of silicon steel is very much restricted. How much? Hardly 4 to 5%, not more than that. Hardly 4 to 5% of silicon is added to the silicon is added to the steel, not more than that. If you add more and more silicon, it is no more core, it will be silicon. Silicon is nothing but sand. The mechanical strength of the core is going to be reduced if you add more and more silicon. That is the reason why addition of silicon is restricted. Addition of silicon is restricted. Hardly 4 to 5% of silicon is added. Not more than that. Okay. So in order to reduce the eddy current losses, we add silicon. Otherwise, we don't. Silicon purpose is not to minimize the hysteresis losses. Silicon purpose is to minimize the eddy current losses. If you want to reduce the eddy current losses furthermore, okay, don't try to add more and more silicon. Please try to go for another alternative method. Okay, whatever I said, these are the core features. You see, the silicon content is 4 to 5%. If you want to go for reduction in eddy current losses furthermore, better operation is laminated steel. Don't use a solid steel, use a laminated steel. Don't use a solid steel, use a laminated steel. Because of lamination, what is going to happen? Area of cross section is reduced. If area of cross section is reduced, core resistance is increased. That means what? Whatever the electron which is existed here, it is confined here only. And it is the moment of electron is going to be opposed by this thin area of cross section. If area of cross section is very thin, electron's movement is very difficult now. If area of cross section is very small, electron movement is very difficult now. Therefore, the strength of the eddy current will still reduces, and therefore eddy current losses further reduces. I am repeating once again, instead of using a solid core, use a laminated core. If you use a laminated core, the area of cross section, lamination means thin sheets, maybe 1 mm, 2 mm thin sheets. If you reduce the area of cross section, resistance increases. Smaller, you take a saline pipe, we will take up IV fluids, saline pipe. The pipe is very, very small. Pipe dia is very, very small. How much amount of liquid can flow? If the saline is placed, it will be existed for, it will be, it will be continued for around 40 minutes, 20 to 40 minutes. If the pipe dia is more, liquid can flow very quickly, na? Here also, if the area of cross section is very small, the current is restricted, or the current is going to be, the current flow is opposed, the strength of the current is reduced, and hence eddy current loss also reduces. So if you want to reduce eddy current losses, add silicon. If you want to reduce eddy current losses furthermore, go for laminated structures. So maximum, most of all the magnetic paths are, in all the machines are laminated only. Thin sheets only, and apart from the lamination, once you laminate them, there is a first lamination, second lamination, third lamination, fourth lamination. If you bring all the laminations together, if the surface is not smooth, there might be chance of existence of air gap between them, and the electron tries to jump from one lamination to another lamination, one lamination to another lamination, and it leads to sparking. Whenever the electron is jumping from one lamination to another lamination, it leads to spark. To avoid it, what we do? We use here insulation. Between each and every lamination, we will be placing the insulation. What is the insulation? Insulation can be paint, insulation can be a paper, insulation can be a varnish coating. It's like a paint only, or otherwise oil. We generally place paper, or otherwise we generally go for painting, varnish coating. Now, if one lamination is there, one sheet is there, on this paint has to be placed. Next, one lamination. On this lamination insulation has to be placed. Next, one more lamination. On this, insulation has to be placed. So, lamination, insulation, like that. Okay. So, totally I can say that actually the core has to be iron or otherwise steel material. 100%, this core has to be 100% steel or 100% steel or iron. But because of lamination, along with the core, we are getting insulating material also. Now the core percentage is going to be reduces. The magnetic path percentage is going to be reduces. It is no more 100%. Along with the core, insulating material is also there. Okay, we define with the stacking factor. This laminations, this part, especially body centered cubic structure, the silicon grain shape, we will discuss when it comes to the induction motor. Okay. So, we will be discussing about the availability of the core. The availability of the core, you see, iron factor, stacking factor, net cross section area of the core, AN, by gross cross section area of the core. Net cross sectional area is nothing but area occupied by the magnetic material only. Area of magnetic material. Gross cross section nothing but area of magnetic material plus area of insulating material. Now the denominator part is anyhow, let me take up magnetic material. If I take up 90%, insulating material will be 10%. So totally on the whole it will be 90%. Stacking factor or the iron factor will never be equals to 100%. Stacking factor or iron factor is not equals to, stacking factor or iron factor never be equals to 100%. It will be less than 100% only, because the iron has in the core, complete iron is not there. In the core, along with the iron, insulation is also there. That's the reason why iron factor, availability of iron is not 100%. Along with the iron, insulating material is also there. The value range is 0.5 to 0.95 is there, but we prefer for electrical operations 0.95. For communication purpose, for that purpose we go for what we can say pulse transformers, communication transformers. For that, in that case, we'll go for 0.5 range. Okay, all right. Now see, one more point I wanted to say here. If you look at the shape, as we are going for laminations, the shape of the laminations are looking like L shape, 7 shape, or otherwise W shape and I shape. Okay, like this. The shape of the laminations are L7, WI, or otherwise M. You can also go ahead with the here W. It is M and I. It is ulta 7 and ulta L, reverse L, reverse 7. That means if the first layer is L and 7, second layer has to be reverse L and reverse L and 7, reverse L and reverse 7. Why? If you place the laminations like this continuously, L7, 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 if you place like this, at this corner, there is a chance of leading to air gap. There is a chance of getting air gap. Okay, and to avoid the continuity air gap, in order to avoid the continuity in air gap, you see, first maybe L, reverse L, and then legs later out, you see. And at each and every joint here, at each and every lamination, we will be providing a joint. At each and every lamination, we will be providing a joint. Why? If you don't provide a joint, mechanical strength is not good now. The two pieces has to be joined so that mechanical strength of the core will increase. So butt joints are preferred to increase the mechanical strength. Butt joints are preferred to increase the mechanical strength. Okay, so this is how the laminations are going to be placed. 1, 2, 3, 4, 5, 6 alternate laminations we are going to place. This is like a core type construction and this is like a shell type construction. Okay, now we have seen already stacking factor. The core staggering here. Core staggering process is very, it should be tight. While bringing the laminations, one laminations to another lamination, to form a core, bunch of laminations, bringing all the laminations together to form a core is nothing but core staggering. If the core staggering is not properly done, tightly done, what is going to happen? If core staggering is not properly done or not tightly done, if staggering not tightly done, then there will be an existence. If this is a lamination, I have to bring the next lamination, I have to put it very tight. Next lamination I have to bring and I have to put it tight. If it is not tight, what is going to happen? There is a chance of existence of air gap between the laminations. Okay, if it is not tightly done, if not tightly done, then it leads to air gap between the laminations. Okay, if it leads to air gap between the laminations, okay, what is going to happen? Air gap will possess the reluctance. Air gap increases the reluctance of the core. If the reluctance increases, what happens? We know flux is equals to MMF by reluctance. Same as like Ohm's law in electric circuit. In electric circuit, I is equals to V by R. Potential difference divided by resistance. In magnetic circuit, flux is equal to MMF by reluctance. MMF I can write it as N into I mu divided by reluctance. Because of air gap between the laminations, air gap increases the reluctance. If the reluctance increases, flux establishment in the core decreases. But a transformer wants to maintain the constant flux. Transformer is actually a constant flux device. We will discuss in the operation. If it wants to maintain the flux, as constant, its value has to be increased. To maintain the flux as constant, how to increase? Number of turns cannot be increased. The transformer will draw more magnetizing current. If the core staggering is not done properly, then the transformer will draw more magnetizing current to establish a constant flux line. This is a drawback for us. If the magnetizing current is going to be more, it leads to low power factor. The only remedy to overcome the poor core staggering is go for tight riveting. make it tight. There is no other option. If core staggering is not properly done, there is one more option, is one more way is there. Lamination, this is one more problem is there. This is one sheet and this is another sheet. One sheet, another sheet. If they are not properly riveted, whenever the flux lines are interacting with the sheets or whenever the flux lines are establishing through the core, because of alternating force, that means what? Positive half cycle, negative half cycle, positive half cycle, negative half cycle. Because of continuous reversal of flux lines, there can be a chance of a small mechanical force developed on the sheet. Why? There is a chance because of continuous reversal of flux lines, the sheet dimensions are going to be slightly increases or slightly decreases or increases. If the sheet dimensions are going to be changes, then the sheet can collide with the neighboring sheet. That lamination can collide with the collide with the neighboring sheets, and because of that small collision, it leads to a small noise, and that noise is called as humming noise. Not hissing noise. Hissing noise is the noise created on the overhead conductor due to corona effect. Humming noise is like that. Hum. It's a magnetic hum. It is because of magnetostriction. Magnetostriction means the magnetic path undergoes change in dimensions, and that is due to alternating flux lines. So we have discussed about this point also. Here, if the core staggering is not properly done, there is a possibility to get the air gap, small air gap between the laminations, and it leads to more reluctance, therefore increases the excitation current, that is I mu is going to be more. Okay, and one more thing is it leads to noise also, that is called magnetic hum. How to avoid this thing? The only thing is you need to do it. To avoid this, tight riveting is done. Tight riveting can avoid. Okay, tight riveting can be avoiding this magnetic hum. So this is about the core construction. Please try to have a look at this one. We have discussed about core, what is the intention behind the core, why we are placing the core. Okay, the main intention behind the core is to have low reluctance path and high permeability, so that more flux lines can link with the second coil. Coefficient of coupling is going to be enhanced. EMF can be induced more, power transfer can be enhanced. Okay, so that's the main intention. How to design that? Use a ferromagnetic material. Ferromagnetic material is steel, not silicon steel. See, steel. But why are we adding silicon? To minimize eddy current losses. If you want to minimize eddy current losses, furthermore, go for laminations. If you go for laminations, between the laminations, if you go for lamination, air gap might be created while forming the core. In order to avoid the laminations, fill the gaps with the paints, varnish coating and paper. So if you fill the gaps with the paper or varnish coating, then the core is not 100%. The core is going to be less than 100%. Okay, right. Here the lamination shapes are going to be L or I, the laminations are going to be alternate laminations. If this is the first lamination, second lamination is this one, like this. Third lamination is this one. Fourth lamination is this one, and even in the same shell type construction also. Alternate laminations leads to uniform air gap, or even if there is an air gap chances existed, that leads to normalized air gap. And between each and every lamination you can place the insulating material and you can fill it. Okay, so we have discussed about gross iron factor also. That iron factor will be definitely less than 100% only, because insulating material is there na. So while if core staggering is not properly riveted, if properly not done, it leads to magnetizing current and it leads to magnetic humming also. Okay, that can be minimized with the help of tight riveting. All right. So we will be discussing about next part in the next session. Okay.